An important aspect of chemical reactions is that they're often accompanied by some kind of energy transfer. We're going to be covering that in this module, but to get started with that, we need to understand something about heat and temperature because they're going to be indispensable tools for us. Our learning goals are to understand how energy can be exchanged via heat flow between objects. And we also want to understand what temperature means and how the different scales are related. So let's talk in general about energy exchange. First, I want to define thermochemistry. It's a term that we use a lot when we talk about the energy changes that accompany chemical reactions. It's basically the study of energy flow during reactions. Now, in order to understand and get some of our terminology straightened away, I want to consider the following scenarios. Okay, we're going to always separate a system, which is typically going to be a chemical reaction of interest, from surroundings. And the surroundings are going to be basically everything else in the universe, although sometimes the surroundings could be a small select part of the universe that it just happens to be adjacent to the system. Now, we're going to care about a couple of different possibilities. One is where energy flows into a system from the surroundings. Now I'm going to use the letter Q to denote heat. It's a common abbreviation used in chemistry and physics. And when Q is greater than 0, we say that heat has been added to the system. So heat has flowed into the system and added energy to the system. So we might draw a graph with energy as the vertical axis where we start at one energy and we go up to another energy. This would be another way of specifying the same sort of change. We go from a low energy to a high energy. Energy has been added to the system. Now the opposite of this situation is when energy flows out of the system into the surroundings. In this instance, our heat, Q, would be less than 0, and it denotes heat being lost by the system. So now if I draw, again, my vertical axis for energy and a couple of energy levels, I would show energy leaving a high level and going to a lower level. So these are the two possibilities that we're mostly going to see in this course dealing with heat flow. Now, the last case that we just talked about is called exothermic, and that's when system releases energy to surroundings. So if the system is losing energy, it's going to a lower energy, it's releasing that energy to the surroundings, and we say that that's exothermic. The heat is leaving or exiting the system. If energy is entering the system, if heat is entering the system, then we call that an endothermic process. Heat is going in from the surroundings into the system. Now let's look a little bit at a microscopic level. There are a couple of mechanisms for heat flow that you should be familiar with. The first and perhaps most important is thermal contact or conductivity. If we have thermally conducting material, it can lend heat from it to something else, and it's usually caused by physical contact. Another form of heat flow is convection, and that's when heat is carried by a fluid, and that fluid can be either a liquid or gas. And you might think of this as being like the old water heaters in old buildings where they would heat the water up and then ship it through pipes to all the rooms, and it would go through a radiator that had all these pipes in a coil, and that's what heated the room. Well, they were carrying heat from the boiler up to the room through this fluid that was running through the pipes. A last form of heat flow that we might concern with is radiative transfer. This means that the heat is carried by light. If you've ever sat outside in San Antonio on a hot summer day, you are very familiar with radiative transfer of heat. Now, another way we can think of these things is like going to a large athletic event and sitting in the crowd. There's a lot of different ways that you can derive energy from being at that event. For example, if people are jostling you, they're getting up to go to the restroom or they're getting up to go get refreshments, that's a way of doing thermal contact that would cause you to gain energy because they keep bumping into you. If the crowd is doing a wave or something like that, that might be more like convection. That might be heat carried because you're moved to join the action, to join the wave by the stuff going on around you. If something exciting happened on the field and you see it, then that gives you energy and you start jumping up and down. That's a way of radiative transfer. What you've seen has caused you to, what you absorbed through your eyes has caused you to gain energy. All right, so let's talk a little bit about temperature. Now, I'm going to give you a definition of temperature that may be unlike one that you've seen before. I'm going to say that temperature is basically a measure of the kinetic energy of particles. I want you to think about that for a second. What is kinetic energy? Kinetic energy is the energy of motion. So if temperature is a measure of that kinetic energy, that means temperature is somehow intimately associated with the motion of particles. The higher the temperature is, the faster that motion is. So we might say the higher the average kinetic energy is of the molecules. If it's lower temperature, then that means they're moving slower. They have a lower average kinetic energy. Now there's actually an equation that relates these two to each other, and it looks like this, where kinetic energy, the average kinetic energy, is equal to 3/2 kT, where T is the temperature. K is a constant. It's the Boltzmann constant. It has a fixed value. 3/2 obviously is just a number. So this particular equation tells us very much that average kinetic energy is exactly given by temperature and vice versa. Now, I think we need to talk a little bit about temperature scales because there are three that are in common use in America. There's the Fahrenheit scale. We're about the only country left that uses it, but I want to tell you something. We're not going to use it in this class. We're going to be dealing mostly with the other two. Now, in order to understand Fahrenheit, I'm going to draw just a generic temperature scale. I'm going to set a firm end on the left-hand side, and temperature increases as you move from left to right. And the basic ingredients for a Fahrenheit scale is that it assigns definitive temperatures at two different points, one where water melts and one where it boils. The one where it melts we call 32 degrees Fahrenheit, where it boils is 212 degrees Fahrenheit. So there's a difference of 180 degrees Fahrenheit between those 2 points. Now a second temperature scale that we run across is centigrade, and it uses those 2 points as its reference as well, although it's going to set its 0 at the temperature at which ice melts. So the place where we have 32 degrees centigrade is going to be 0 degrees Celsius. But it's going to set 100 degrees Celsius where water boils. So we're going to have these 2 points set in the centigrade scale. Now, due to these relationships, since 0 degrees centigrade is exactly the same temperature as 32 degrees Fahrenheit, and 100 degrees centigrade is exactly the same temperature as 212 Fahrenheit, we can actually relate these 2 degrees to one another. And in fact, the increment of 1 degree Fahrenheit is equal to 5/9 of 1 degree centigrade because of this relationship. Now the third temperature scale, and this is the one that we're going to prefer in this class, is the Kelvin scale. It has as its reference absolute 0, and that's down here at this far left end. Now I've put that hard margin there for a reason, because according to the laws of physics, we cannot go below absolute 0. It is the absence of all motion. So everything ceases to move at 0 Kelvin. Now we also, in the Kelvin scale, we set the increment of 1 degree equal to the increment of 1 degree centigrade. So by doing that, it means that now in Kelvin, the place where ice melts is 273.15 Kelvin, and the place where water boils is 373.15 Kelvin. All right. Now this means perforce that the the absolute 0 of temperature scale is going to be minus 273.15 degrees centigrade. And if you use the conversion between centigrade and Fahrenheit, you can learn that it also corresponds to negative 459.67 degrees Fahrenheit. But I don't know of anyone that's going around trying to get to negative 460 Fahrenheit. It's not a possibility. So hopefully this gives you an idea of how the temperature scales relate to one another. They're just different ways of marking down increments of temperature along the same scale.